All right, how's everybody doing this morning?
It's a day.
It's a day, another day. All right, here we are. Okay, so today we're going to start with a review of BowBots, just kind of quickly summarize some of the stuff that we learned. And then we're going to go on and talk about our main topic today, which is resistance. So remember, resistance is one of the three main descriptors of electricity. We talked about voltage, current, and resistance. So this is one of the most important things about electricity. So we'll talk about what resistance is, why we care, how resistors actually work, and then we'll look at the color codes on resistors. So up until this point, you've used some resistors in your projects, and you've seen that they have those color bands on them. And we've said that those color bands actually mean something. They tell you what value those resistors are, but we haven't been able to figure out how to read them yet. So today we're going to talk about how that actually works. And then we're going to go on and talk about multimeters. So this is one of the coolest things, one of the most important topics in electronics is starting to use multimeters, because once you start to learn how to use a multimeter, you can actually try stuff out and figure things out for yourself, right? Up until this point, I've been standing up here and talking at you, and you just kind of had to take my word for it, and you had to believe me, but you never know. I could have been lying this whole time, right? How would you know? So after today, you can actually try it out and test it out for yourself and figure out, what's true and what's not, okay? So I'm going to start showing you how to use multimeters so that you can do that. So we'll talk about what they are, why they're so important, and then I'm going to do a demonstration measurement on how we can use a meter to measure a resistor, and also how we can compare that measurement that we make to the color code on the resistor itself, okay? And then we'll go on and do a preview of today's lab. So in today's lab, no surprise, you're going to be using multimeters to check resistance. And one special type of resistance measurement is called a continuity check. That is where you check a wire or a cable to make sure that it's working properly. So when we say working properly, we mean that things that are supposed to be connected together are connected together, and things that are supposed to be separate from each other are not connected accidentally, okay? So this is a type of check that would be very useful if in many different fields. So if you're trying to work on musical equipment, you could check cables that are running from your instrument to your amplifier, say. Or if you're installing wiring in a house, you could check the wires that you put in to make sure that they are working, that there's no shorts where there shouldn't be any shorts, okay? So this is a very common type of check, and I'll show you how we can use the meter to do that. And so we'll do some resistance measurements and also some continuity checking in our lab. So are there any questions about that before we get going? Okay, cool. So then I wanted to start with a quick review of BowBots. So over the last few classes, we've been working with these BowBots, and we've seen a lot of cool stuff. We made some lights go on, we've made motors move, and finally you made wheels turn, and you actually got your robot to navigate on the course. So those were all awesome things. We really like the kits for that. Starting now, we're going to be moving on, and we're going to be working on other things. So we're now done using these kits. So what that means is that during this class, at some point, I'd like you to grab your kit and make sure that you disassemble everything that is in there and put it back in the bags where it came from. Take the chassis off of the board. Just put it back the way you got it on the first day of class, okay? Because we're done with those for now. We're not going to be using those again this semester, okay? So if you missed a lab over the last couple of weeks since the beginning of class, and you need to make up for one of those. You can still use some parts from one of the kits, but please, today, you and your group should disassemble the parts in your kit so that it's ready for the next group of students to use it, okay? So any questions about the BoBots or any of the stuff that we did with those? Okay. All right, cool. So then let's go on and talk about resistance. So what is it? Anybody remember a simple definition for resistance? Yeah.
A force that counteracts the flow of current.
Yeah, exactly. The force that counteracts or opposes the flow of electricity. So it's what makes it hard for electricity to flow through a circuit. So we also might ask what a resistor actually is. So there are many different kinds of resistors, okay? So in this class, you've seen some of the little resistors that we put in our boards. And those are a very common type of resistor, but there are many other types of resistors as well. So for instance, you have resistors that might look like this, or this is another type of resistor, okay? You have some very large resistors, like this, okay? So that's a resistor. There are also some very small resistors. So if we look at this strip, you might be able to see little black dots on that strip. Each one of those little black dots is a resistor, okay? So, so you can see that resistors can vary greatly in their size and shape. They have all different characteristics. Now, we talk about how much resistance something has, okay? So that's how much it resists electricity, how difficult it makes it for the electricity to flow. So you might think a bigger resistance means a bigger thing, but that's not necessarily the case. In fact, this big resistor that I have right here has a resistance written on it of 12.1 ohms. So this is a resistance of 12 ohms. These resistors are 470,000 ohms. Okay? So these little tiny things have 470,000 ohms of resistance each. And so you can see that size doesn't necessarily correspond to how much resistance something has. You can have resistors this size that are 1 ohm, or up to 470,000 ohms, or even a mega ohm, 1,000,000 ohms. Okay, so you can have resistors that are the same size but very different amounts of resistance to them. So, can anybody think of a reason why you might want to have a very large physical size for a resistor? Yeah.
For like large circuits, because smaller resistors cannot handle the large currents of like the power plant.
Yeah, that's exactly right. Yeah.
I was just going to say heat dissipation.
Yeah, those go hand in hand, exactly. When you have a lot of current, like you said, it creates a lot of heat. And so you need to get rid of that heat. And basically, the bigger physical size you have, the more volume you have to spread that heat over. If you had a little tiny resistor like this, all that heat would be concentrated in a little speck. And so that little speck would get tremendously hot and would probably burn up or melt or destroy whatever is nearby. So when you have a larger thing like this, it spreads that heat over more volume. Also, it has more surface area where that heat can release. And in some cases, like this, you can see that fins have actually been added to give it even more surface area to let go of that heat. So I'll pass that around so you can take a look at it. So then, so if you could use a big thing like that for heat dissipation, why would you ever want to have a little tiny resistor like this? Any ideas? Yeah.
This one is rated for like smaller circuits with like less current, less voltage, so it can handle the high, the small amount of current. So
Right, right. So it can't handle as much current as that. So why would you want something that would handle less current when you could handle more? Yeah.
The size of it?
Yeah.
Too small.
Exactly.
And it'll be too big for a circuit board or whatever.
Right, right. How'd you like to have a cell phone with one of those things inside, right? Yeah, yeah. So so these little resistors are good for a lot of consumer electronics where things are trying to be smaller and more portable. Okay. So this is something in between. So each resistor is rated for how much power it can handle. So generally, the larger the size of the resistor, the larger the physical volume of the thing, the more power it can handle. So this one is rated for 15 watts. This one is rated for 120 watts. Okay. The little ones that we typically use are rated for 1/4 watt. And these little tiny surface mount guys, I don't even know. Does it say on, there was a little piece of tape on there. Does it say power rating? Anything in watts?
It says 470K.
It 0.1 watts. So that's 1/10 of a watt. This is 12 watts. So yeah, you can see that the larger the physical size, the more power it can handle. Okay. So those are all fixed resistors, meaning that they have one value that's set when it's made at the factory, and then that's constant. It never changes. But there are other types of resistors that are variable. Okay. So things like this. This is a variable resistor. So you can actually change the resistance from the one side to the middle by turning this shaft that's in the middle. So when you turn the shaft, what it does is it moves this wiper around. Okay. So the way that this works is that there's a big coil that has resistance in it, and it's wound all the way around this outside shape here. And then you can connect from one end here to the middle, and the middle is attached to this wiper. So when the wiper is all the way over to this side, you have essentially a direct connection from this side through the wiper to your middle point. And so you have essentially zero resistance there. So when you turn the wiper all the way over here, you have zero resistance. When you move the wiper all the way to the other side, now the electricity has to go through this whole coil before it gets to the wiper and comes down. So then it has to go through the whole resistance. And this one is 400 ohms. So if you move the wiper all the way over here, it's 400 ohms. If you move it all the way here, it's 0 ohms. What do you think you'd get if you put it right in the middle? Yeah, about half, or about 200 ohms. Okay, so depending on where you put this wiper, you can change how much resistance you have from one side to the middle. Okay, so this is called a potentiometer, and this is actually a device that is used quite commonly as a volume knob. Okay, so if you have a stereo or something like that, and you want to change the volume, oftentimes you turn a little knob, and what you're really doing is you're turning the knob on a potentiometer like this. Usually it's much smaller. You know, it's small enough to fit inside your stereo. These are often also used on electronic instruments like electric guitars or things like that. So if you have an electric guitar and you've got a couple of little adjustments down here, what you're really doing is you're turning a knob on a potentiometer like this. Okay, and so you're changing that resistance. So I'm going to pass this around. Here, check that out. So that's a potentiometer. There are other versions of potentiometers too. So this is the same type of thing, but a little bit smaller. This is a little bit smaller still. So you can see there are many different versions there. Here, we'll pass these around this way. And then this is the same type of thing, but it is just, oops, it's in a straight line. Instead of going bent around in a circle, this is a big wire wrapped around a straight form. Okay, so this is a little potentiometer that's just in a straight line. But it's the same idea. You can adjust the amount of resistance from one side to the middle by moving this middle section back and forth. Okay, so I'll pass that around too. So that's what resistors are. And you'll also have resistors that are more commonly shaped. So kind of like the little shape that we have for the resistors that we use in the back. These are a little line that have two wires sticking out the ends. And you can see that these resistors have little color bands on them like the other ones. And we'll talk about those color bands today and what they mean. Okay? So again, these resistors can have all different values, and the size mostly corresponds to how much power they can handle. Okay? So you can check those out. All right. So that's what resistance is. It's opposition to the flow of electricity. And now you've seen what resistors actually are. They come in all different shapes and sizes for all different purposes. Okay? So why do we care about this? Well, we care. We've already talked about some of the reasons why we might put a resistor in a circuit. So remember the first day of class, we drew that circuit and we had a power supply over here and then an LED and then a resistor. So why did we have the resistor in that circuit? Yeah, that's right. We wanted to limit the current so we didn't drain too much power, too much current too quickly from the battery. And also, we wanted to limit the electricity so that we didn't heat up the LED too much because that could damage or destroy it. Okay? So those are common uses and common reasons that we use resistors to limit the current. Another reason that we can use resistors is that we can change voltage. We can use them to change voltage. And we'll talk more about this later in the semester. But if you have a power supply here and then you have two resistors that are the same value, say this is a 5-volt power supply here, what happens is that right in the middle of this, these two resistors, you get half of the voltage. So that would be 2.5 volts there. Okay, so if you need a circuit that can change the voltage, you can use resistors to do that as well. So those are a couple of reasons why we care about resistors, why they're important and how we can use them in our circuits. Okay, we'll be talking more about this as we go through the semester. Okay, so anybody have questions about why resistors are important? Okay. What are they made of? I'm glad you asked. So, so that's what I'm going to talk about next. So, how do they actually work? Yeah, what are they made of? Well, it turns out that they can be made of all different kinds of things. And I actually have a book here that goes into some of the different ways that they're made. This is a super cool book. It's called Open Circuits, and what it does is it actually takes all kinds of common electronic components, and the person who made this book cut them open so you could actually see what's inside. Okay, so I'm going to pass this around and show you some of the examples of the different types of resistors here. But let's see. So they have some of the potentiometers like we have here. But yeah, you can see that there are even smaller potentiometers. These are little ones that go on top of circuits. And then you can see inside of some of those. And you can basically, there are a couple of common examples of how resistors are made. So one is called a carbon film resistor, okay? So I'll pass this around. So basically the way that this is made is that you have this material, which is a carbon film. It's like a strip of material that has carbon imprinted or impregnated into it. And that carbon allows some of the electricity to flow. And then that carbon is wound around, that carbon strip is wound around a form. So this is essentially like one of those, that straight, like one of these guys, okay? But instead of just a wire, it's a carbon film that's wrapped around the form, okay? So that's one type. Another type of resistor is called a wire wound resistor, which is essentially what this is. This kind is also wire wound, but this book shows it cut in half, so you can actually see what's going on inside there. But yeah, essentially it's the same sort of thing, but encased in ceramic, okay? And then another common type of resistor is it's called a carbon-based resistor. And so basically what happens with these is that you have a mixture of carbon, which conducts electricity, and clay, which kind of holds things together. And these compounds are mixed together and then formed into little resistor shapes, and wires are stuck in the ends, and that's how you make your resistor. So the cool thing is that companies can use this process to make very different values of resistors. So if they want a resistor that has very little resistance, they just make their mixture mostly carbon so that it's very easy for the electricity to flow. And then if they want a resistor that's got a very high resistance, they just change their mixture so that it's mostly clay. And then that makes it holds things together, but it makes it a lot harder for the electricity to flow. So just by changing this mixture, they're able to change the resistance of the little component that they make. Okay? So so I'll pass this around. The resistors start around page 16 here, and they go up to about page 30. Okay, so we'll pass that around, and you can check that out. Okay, so that's how resistors are actually made. There are all these different types of processes, and but they are basically put together by. And the value of the resistor is set by either increasing the amount of carbon or decreasing the amount of carbon that allows the electricity to flow. Okay? Does that kind of answer your question? Yeah. Okay. All right. So that's how resistors actually work. So any other questions about that?
Professor,
Yeah.
also the temperature sensor and departure sensors is made of sensors. How are they works?
Temperature sensors and what kind of sensors?
Departure.
Departure sensors?
When they detect the moving.
So temperature sensors come in a number of varieties. One of them is called a thermistor, which is basically a resistance-based temperature sensor. And so what happens with those is that certain materials change their resistance based on the temperature around them. So like when it gets hotter, they have more resistance. When it gets cooler, they have less resistance. And so if you can measure that and you know exactly how much resistance there is when it's 72 degrees outside, then you can use those sensors. You can measure their resistance, and that'll tell you what temperature it is. So maybe they have a 10 ohms when it's 90 degrees out, and 8 ohms when it's 70 degrees out, and so on. If you can make that measurement, then you can tell how warm it is outside. Departure sensors, I'm not quite sure what you mean by that. So like
When moving the lights around, please.
Like
place,
when you depart a room.
Yeah.
So there are other types of resistors that are sensitive to light. Those are photoresistors or phototransistors. And what happens with those is that when people are walking around a room, they might cast a shadow on this little sensor. And when that happens, the resistance might change. And so there's a little microcontroller inside your switch that looks for those changes. And if no change happens within, say, 5 minutes, then the sensor says, okay, nobody's moving around here, the room must be empty, so I'm going to turn off the lights. So again, there are a number of different types of sensors, but one of them is a photosensor like that. Yeah. So, yeah, other questions? Okay. All right, so that's a little bit about how resistors actually work. So then let's go on and talk about color codes. So the color codes, before I go on, I wanted to tell everybody that we're going to have homework today. So I know we haven't really had homework in this class so far, but starting today there will be some homework assignments. So today's homework assignment is a color codes quiz. So we'll talk about how we read color codes in class today, and then for homework I'd like you to do the color code quiz on Canvas. Okay, so this is, you go into Canvas, you look for quizzes, there should be a color codes quiz, and this will just be a way to practice your knowledge of how to read color codes. Okay? All right, so the way that color codes work on the resistors that we use in this class is that there are three values written, and then one tolerance. So there are 4 bands altogether. 3 of them represent the value of the resistor, and the last one represents the tolerance. So the 3 bands that represent the values, the first 2 represent the resistor size, and then the last one represents the first 2 represent the resistor digits, and then the last one represents the number of zeros. So 2 digits and number of zeros. Okay?
Professor?
Yeah.
About the color code quiz, I
Yeah.
don't see it under the quizzes. Is it?
Okay. I will double check on that. Yeah.
Because all I see is metric, rounding, Ohm's law, parallel resistance, zeros of resistance, and Watt's law.
Okay, so I'll check on that when I'm done with the lecture, but thank you for telling me. Okay, so, all right, so the 3 values, the first 2 represent 2 digits, and then the last one is the number of zeros, okay? So, but in order to understand what these numbers actually are, we have to understand what the colors represent. So basically, each there are 10 different colors that we use, and each one represents one of the digits between 0 and 9. So the colors go like this. It's black, brown, red, orange, yellow, green, blue, violet, gray, and white. And they represent the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay? So when we're looking at a color band, if it's an orange color band, it represents the number 3. Okay? So you will not be required to memorize the color code numbers for this class. It's not necessary, but it can help to speed things up. So if you want to memorize it, there is something called a mnemonic device. That's a device that helps you to remember something that you can use to memorize these colors. So the mnemonic device that I remember is bad boys, race, our young girls, but violet generally wins. Okay, so the first letters of these words correspond to the first letters of the colors. So if you can remember that, you can remember, it can help you to remember the colors there. Okay? All right. So now we know what the colors mean. So let's do a couple of examples of converting resistor color codes into actual values. Okay? So one of the colors that, or color code combinations that we have seen is yellow, violet, and brown. So we saw that on a lot of our resistors that we were using with our little LEDs in our circuit so far. So let's see how we can translate that into an actual value. So the resistors might have actually been yellow, violet, brown, and then a gold band on the end. Okay? So, so we said that, so first of all, let's figure out what these colors represent. So what is yellow? 4, perfect. And then violet, 7. And then brown, 1, okay. And then this gold is a tolerance band. So the tolerance is how close something has to be to what is specified. Okay, so so for tolerance, basically the reason that we have tolerance is because nothing in this world is perfect. Okay, so so imagine I asked you, we were building a house, and I asked you to cut me a board that was 10 feet long. Could you ever cut a board that was exactly 10 feet long? No. You could get darn close. Maybe you could get within a 16th of an inch or a 32nd of an inch. That'd be plenty close for building a house. So that'd be great. But if I were to get in there with a measuring tape, I could maybe see that board was just the tiniest little hair off from perfect. And even if it looked perfect on a measuring tape, I could get in there with my laser measuring guide and check it, and maybe it was 1/1000th of an inch off. So basically, nothing in this world is perfect, and the harder you try to make it perfect, the more difficult it is, and so the more expensive this thing becomes. So if you were to try to cut this board so that it was within, a 1/1000th of an inch, you'd have to spend all day doing it. You'd have to set up a really precise jig, and you'd have to cut it just right, and maybe file it down and then sandpaper it down. So it would take a really long time. And so if I'm building a house, I don't want you to do that, all right? I want it to be 10 feet plus or minus, a 1/4 inch. That's close enough. If you can do that, that's fine. So that amount of wiggle room that is acceptable to me, that's the tolerance, okay? That's how close I want it to be. So these bands at the end represent the tolerance. So for tolerance, a gold band equals 5%. Silver equals 10%, and none, if there's no band, that means 20% tolerance. Okay? So this last gold band represents 5% tolerance. Okay, so if we have a yellow, violet, brown, gold resistor, we say that those numbers represent 4, 7, 1, and 5%. Okay? But we're still not at an actual value for this resistor yet. So let's do that. So we said that the first two numbers are the first two digits of the actual value. So that becomes 4, 7, and then the last number is how many zeros you have after that. So in this case, we have 1 0. So that'd be 470 ohms. So this color code is telling me that this resistor is 470 ohms. But is it going to be exactly 470 ohms? No. Right, we have this tolerance on there. So it's saying it's 470 ohms plus or minus 5%. Well, let's dig into that just a little bit deeper. So if we want to figure out what that really means, we have to figure out what is 5% of 470. So 5% of 470, that's equal to 0.05 times 470. .05 times 470. Does somebody have a calculator? What does that come out to be?
23.5 ohms.
Okay, so 23.5, we'll call it 24 ohms, okay? So this is 470 plus or minus 24 ohms, okay? So what would be 470 plus 24, or minus 24 ohms?
446.
So that would be 446 ohms would be the lowest value you could have. And what would be 470 ohms plus 24?
490.
Yeah, 494. So that's what this color band combination is telling us. It's saying that it's a 470 ohm resistor plus or minus 5%, which means really it could be anywhere between 446 ohms and 494 ohms. Okay? And if the resistance, the true resistance, falls somewhere in that range, then we say that the resistor is in tolerance. It's within the specified limits of what it could be. But if it got damaged or something and it was outside of this range, then we would say that it was out of tolerance. It's not where it's supposed to be. Okay?
Professor?
Yeah.
Right, I'm lost at the step where it's 471. How does it become 470?
Right. So when we have the three values, the first two digits represent the first two digits of the value. So that's the 400, the 4 and 7. And then the last one is the number of zeros after those first two. So in this case, there's 1 0. Yeah. Yeah. So you might say, well, why do that? Why not just have the actual value there? The problem with that becomes when you have really big numbers like million. You know, a million is 1 followed by 6 zeros. So you'd have to have like 7 colors on your resistor, and you can't really fit that many resistor or bands onto a little tiny resistor body. So we do it this way. Okay. So why don't we do another example here to kind of help us go through this again. So let's say we had brown, black, red. Okay? So we had a resistor that was brown, black, red, and say a silver tolerance band. Okay? So what does brown represent?
1.
Yeah, 1. And then black represents what? And then red is 2. And silver is what tolerance? 10%. Perfect. So we say that these first two numbers represent the first two digits. So that's 1 0 and then followed by 2 more zeros. So that's 1,000 ohms plus or minus 10%. Now, 10% of 1,000. Yep. So this is 1,000 ohms plus or minus 100 ohms. So that's 900 ohms up to 1,100 ohms. Okay? So those are the values, that's the range of values that would be acceptable for a resistor that's brown, black, red with a silver tolerance.
The range
From 900 up to 1,100. Yeah. Mm-hmm. So if the resistor fell anywhere in that range, it would be in tolerance. If it was outside that range, it would be out of tolerance. Okay? What if we wanted to go the other way? Could we go take a resistor value and then turn it into a color code? Why don't we try that? So let's say I have a 35 35,000 ohm resistor. And I wanted to figure out the color code for that. Okay? So what would be my first color here? Orange, perfect. So the 3 is orange. And then the 5, green, good. And then I have how many zeros? 3 zeros, so orange, okay. So that would be the color code for a 35,000 ohm resistor, orange, green, orange, okay? Yeah.
Is it implied that there's nothing on the last band that's plus or minus 20% for the tolerance, or is it just like, do they have some other symbol that signifies that?
Yeah, so if there is no color band, then yeah, that implies that there's a 20% tolerance. Yeah. Hmm? Yeah. Other questions? Okay. Yeah, so that's how color codes work. Should we do one more example? Sure. Okay. One more. All right. So let's say I have a 10,000 ohm resistor. This one's a little tricky. Okay. So what is the first color that I need here?
Brown.
Yep, brown. Yep, and then the next one is black. And then the tricky part is how many zeros should I have for the last value there?
40.
Right. So it's kind of tricky because you might look at this and say, okay, there's actually 4 zeros here. But what happened is that this second digit already took care of this one. So we only have to account for the last 3. So then what's the number for, or the color for 3?
Orange.
Orange, yeah. So that's how we would do the color code for a 10,000 ohm resistor, okay?
Tolerance is, we take it like.
Oh, yeah, so if there were, right, if there was no, say we had no color band there, so then, yeah, the tolerance would be, what? 20%, yeah. I saw another hand? Yeah.
We have to, but it would be notated if there was a band on it.
Yeah.
Okay.
Yeah.
So just by default, if it's just like that, assume there's no band
I mean,
unless otherwise specified.
yeah. Yeah, that's fine. Yeah. Yeah.
Like hypothetically, if it was like an 80 ohm resistor, it would go black and then gray and then black or like brown.
Like an 80 ohm?
Yeah.
Yeah, so let's do that one. So 80, so we have 8 is gray, and then 0 is black, and then how many zeros are there after that?
0.
Yeah, 0. Black, exactly. So that's how we would do that one. Yep, good question. Other questions? Okay. All right, so that's how color codes work. So now hopefully you can have an idea of how you can read those resistors. Now, some resistor, the vast majority of the resistors that are commonly used are like this. Most of the resistors we use in this class work this way. But there are some high precision resistors that are kind of blue colored, and they actually have 4 color bands plus a tolerance. So those are called 4-band resistors, and they have a slightly different code. So if you see a blue one, the code is a little bit different, but I don't want to go into that right now. So most of the resistors that we use work like this, and so that's what we care about. Okay. All right, so then let's go on and talk a little bit about multimeters. So like I said, multimeters are super cool because there are measurement devices that let you actually check your circuit by yourself. So you don't have to rely on me or anyone else to tell you what's going on. You can actually make the measurements yourself. So let me grab one of these here. All right. There we go. And we'll get a resistor. All right. Okay, so this is a multimeter. So multi means many, and meter means measure. So a multimeter is literally something that measures many different quantities. So it can measure voltage and current and resistance. And then depending on the meter, there might be other things that it can measure. Like these can measure capacitance and inductance as well. They can even measure frequency and duty cycle and things like that. So they can even measure transistors too. So a multimeter is something that measures many different things. If we look at the multimeter, it looks like this. We have a screen at the top that displays the values. We have a dial in the middle that sets the type of measurement that you're going to make. And then down at the bottom, we have these ports where you can connect your leads. So the leads are these long wires that go from the meter to whatever you're trying to measure. The way that you connect this is that the black lead always goes in the port that's labeled common. So COM is right there. The black lead always goes into common. And then the red lead can move around to these other ports depending on what you're trying to measure. So over here, that port is labeled V and omega, so that's where you measure volts and resistance. So if you want to measure one of those things, you put the red lead in that port. This port right here is labeled MA for milliamps. So if you want to measure small currents in the milliamp range, you put the red lead there. And then this port over here is labeled 10A. So if you want to measure larger currents up to 10 amps, you put the red lead there. Okay? So again, the black lead is always connected to the common port, and then the red lead moves around to these other ports depending on what type of measurement you want to make. Okay? So in so that's what a meter is. It's something that measures many different quantities. Why do we care about these? Well, these are some of the most commonly used pieces of equipment in electronics. So regardless of what field you go into, whether it's music or working on cars or installing wiring in houses, electrician, or working on medical equipment, all of these different types of fields use multimeters. They're the most commonly used instrument in electronics for good reason, because they measure these fundamental quantities that we care most about: voltage, current, and resistance, and then some other things thrown in there too. So these are super handy, and they're the fundamental properties of a circuit. So these are the things that you care most about. So we care about multimeters because they allow us to make these measurements that help us to figure out what's going on inside of our circuits. Okay? So So let me do a demonstration of how we would actually make a measurement here, okay? So, so I brought with me a little resistor. Now, where did I put it? Here we go. All right. So, this little resistor, I believe that the colors are red, red, red. Okay, these resistors are very, very small. You can see, and so sometimes it can be difficult to see the colors clearly. So if you're having trouble seeing the colors, one trick is you can use a cell phone and kind of hold the resistor up close to it and either take a picture or just look at it through the cell phone. So that's one way to do it. So I believe that this one is red, red, red. So first of all, let's try and figure out what value that represents, and then we'll measure this resistor with our meter and see if the resistor is actually within tolerance. Okay? So this is red, 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 and then the band, the tolerance band is gold. Okay? So what color does, or what number does red represent? Yeah, so this is 2, 2, 2, and then gold. What was the tolerance value for that? 5%. Perfect. So, so we know the first two digits of the number are 2 and 2, and then we have 2 zeros after that. So that's 2,200 ohms plus or minus 5%. So I want to know what 5% of that is. So one trick to do that is that it's easy to figure out what 10% of that would be. You just take off the last zero. So 10% would be 220, and then 5% is just half of that. So 110. So 5% equals 110 ohms. Okay, so then this actual range would be 2,200 minus 110 would be the lowest value you could get. So what would that be? Yeah, 2,090 ohms. And then the highest value would be 2,200 plus 110. So what would that be?
310.
Yeah, so 2,310. So that is our range for this resistor. So somewhere between 2,090 and 2,310 ohms. That's the values. That's the value range that is acceptable for this resistor. So now let me write this down over here because I'm going to pull the screen down in just a second, and that's going to cover that up. So 2,090 to 2,310 ohms. That's the acceptable range, all right? So now let's actually hook up our meter and make this measurement and see what the value turns out to be. Okay, so this is what the meter looks like. So like I said, up at the top is the screen. In the middle is the dial that sets the type of measurement that you want to make. And then down here at the bottom are the ports. So the first thing we're going to do is we're going to hook up our leads to our meter. So we said that the first thing is that the black lead always goes in the common port. So we're going to push that lead into the common port there. And then the red lead goes to one of these other ports depending on what type of measurement we want to make. So in this case, we want to measure resistance. So I'm going to put this red lead in the right-hand port that is labeled with the omega symbol for resistance. Okay? So now my leads are connected. Now I need to put this dial into the correct setting to make a resistance measurement. So I'm going to turn this dial into this bottom left-hand quadrant that is labeled omega for resistance. So I'm going to turn this down there. And you'll notice that there are many different settings that can be used. And each one of those little settings has a number next to it. So what's going on here is that each of those numbers represents the largest number that you can measure in that setting. And what you want to do is you want to put it in the smallest section that you can that will still give you a decent measurement that will work. So in this case, we think that the resistor is going to be around 2,200 ohms. So would I put that in the 2,000 ohm setting? No, because it's bigger than that. So I would put this in the 20,000 ohm setting. Okay, so I'm going to put that there. And now I'm going to hook up my actual resistor. And this thing is echoing again. Sorry about that. All right. So now I'm going to hook up my actual resistor. So the way that I'm going to do that is that the ends of these leads have alligator clips on them. They're these little metal clips that open kind of like alligator jaws. So what I'm going to do is I'm going to clip one of those jaws onto one side of the resistor, then the other jaw onto the other side of the resistor. And when I do that, I can see that the value up here on the meter comes out at 2.19 kilo ohms. That little K in the top right-hand corner stands for kilo. Okay? And kilo means 1,000. So when you see that K up there, it means multiply this number by 1,000. So 2.19 times 1,000 gives you 2,190. Okay? So this resistor is labeled as red, 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 which means that it's supposed to be around 2,200. But we said that with the 5% tolerance, really, it could be anywhere between 2,090 ohms and 2,310 ohms. So we measured it at 2,190 ohms. Does that fall within this acceptable range? Yeah.
Yes.
So is this resistor in tolerance or out of tolerance? In tolerance. All right. Perfect. So we've checked this resistor, and it falls within the acceptable range. It's an intolerance component. So a second ago, I said that when you are setting up the meter, you want to put this dial to the position that's as small as possible. Okay? So let me go into that a little bit more. Let me talk about why that is. So first of all, let's talk about what happens when we put this meter into a position where the maximum value is too small. So this is about a 2,200 ohm resistor. What happens if I put it in the 2,000 ohm range? You can see when I do that, now the meter doesn't display a number anymore. It displays this OL. So OL stands for overload. That means that whatever you're trying to measure is too big for this setting. The meter can't measure that value, okay? So if you see OL, it means that you're trying to measure something that's too big for that setting. So you have to go bigger, okay? But then you might ask, well, these other settings up here if I move it up 1, I could go up to 20,000 ohms, or 200,000 ohms, or even, 2 million ohms, or bigger, 20 million ohms. Why not just leave the meter in one of those big settings all the time? And then I could measure just about any kind of resistor I want, right? Well, let's see what happens. Did you have a question?
I was just going to try to answer it.
Yeah, go ahead.
I assume since if it's too high, it won't read the lower readings accurately.
Yeah, exactly. It won't be as accurate. It won't be as precise. So right now, in this setting, we see that we're getting a value of 2.19 kiloohms. So that's 2 decimal digits of precision here. Let's see, if we go up 1 value, now we're only seeing 2.2 kiloohms. So we are now only getting 1 decimal point of precision. Okay, so we lost some precision there. And if we go up even higher, now we're down to just a measurement of 2 kiloohms. So you can see every time we go to a higher setting, just like you said, we lose some of that precision, some of that accuracy. All right, so that's why you always want to be in the lowest setting that you can without getting into that overload range, because that'll give you the most precision, the most precise reading, and that's what you want. Okay. All right, so any questions about making those measurements? All right, and then let's go on and do a preview of today's lab. So today's lab is the resistor and DMM familiarization lab, and it starts on page 47. So the first thing that we're going to do in this lab is we're going to do a continuity measurement. So remember, I said at the beginning of class, a continuity measurement is a kind of a special type of resistance measurement. You're using that measurement to check whether a wire is continuous from one point to another. So the way that the meter really does that is it actually checks the resistance from one end of the wire to the other. And as long as that resistance is relatively small, then you know that there is a connection there, okay? So when we're checking continuity, we're really measuring resistance. But there's actually a special mode on the meter to make those continuity measurements, okay? So if we go back here to the meter, you'll notice that in the resistor setting, the resistor quadrant on the meter, down here at the very bottom, there's this little spot that's labeled 200. And that little 200 also has those little lines next to it. And those little lines right here are supposed to represent sound waves. And that's because when we put the dial in this setting and we measure a resistance that is very low, that signifies continuity, this meter actually makes a sound. It's a really horrible, high-pitched squealing sound. You can't miss it. So if I touch the two ends of these leads together, you get that really awful, high-pitched squeal, okay? So the reason for this is because sometimes when you're doing continuity checks, you are, focused down on the circuit and you've got both your hands full and you're really concentrating to look at what you're trying to touch, and so maybe you don't have time to look over at the meter. So that sound can give you an indication that there is continuity. But you'll also notice that the meter shows the resistance up at the top at the same time. So when I connect these together, this has a resistance of about 0.4 ohms, 0.3 ohms, something like that, okay? So So it'll show you the resistance value at the same time that it makes that awful squealing sound. Okay? So that's how we can use the meter to check continuity. So the first part of the lab talks a little bit about continuity checks, and then yeah. And then the second part of the lab asks you to use your DMM to check the continuity of a Cat5 cable. Okay? So Cat5 stands for Category 5. It's this type of cable. This is the type of cable that's commonly used for home networking. So if you have a router that supplies internet, oftentimes the cables that you plug into the back of that router will be Category 5 cables like this. So these cables are made up of 4 twisted pairs of wires, so 8 wires altogether. And what we're going to be doing in the lab today is we're going to be checking one of these cables. So when we check the cable, what we're doing is we're checking that the things that are supposed to be connected together really are connected, and the things that are supposed to be separate really are separate. So the way that we do that is each of these wires has a color to it. So there's an orange wire, a blue wire, a green wire, a brown wire. So we want to make sure that the orange wire on the left side of the cable is connected to the orange wire on the right side. If there's a good connection, that's good. If there is not a connection from the orange wire on the left to the orange wire on the right, we say that is an open circuit. Open means there's an opening between one side and the other. Basically, there's a break in that wire. There's an open gap from one side to the other. So that's bad. So if there's a break, that would be an open circuit. So that would be one type of failure. The other type of failure is if this orange wire on the left is connected to some other color on the right-hand side. So like if this orange wire were connected to the green wire by accident, that is, that's also a failure. And when we have a connection where we don't want it to be, we call that a short circuit. Okay? So if the orange wire is connected to green or blue or one of the other colors, we say that there's a short between those colors. Okay? So we're going to check this cable for open connections or short connections. So what we're going to do is we're going to look at the book, and there's this list that we have to fill out. So the first number that we're looking at is the white and blue wire. So if we look at this cable, you'll notice that there is a wire that is kind of white with a blue stripe on it. So that's the first thing that we're going to check. We're going to look at this white and blue wire, and we're going to connect our meter so that we're going to set it up so that it's in the continuity measuring mode like I showed you just a minute ago. And then we're going to connect so that one lead is connected to the blue and white wire on one side, and then the other lead is connected to the blue and white wire on the other side. And when I do that, we get that horrible squealing sound telling us that there is a connection there. So that's good. All right, so that's the first thing we're going to check. So we know that there's no open circuit between the white and the blue. The second thing we're going to do is we're going to leave this black wire connected to the one side, and then we're going to take the red lead and we're going to check by touching all of the other leads or all of the other wires on the other side of the cable. Okay? And by doing that, we're checking to see if there are any short circuits. where, you know, this blue and white wire might be accidentally connected to one of these other wires, okay? And so in this case, there are no short circuits and there's not an open connection. So we would say that this white and blue wire is good. So we'd put a little checkbox there, okay? The next thing is there's a typo in this book, okay? So right here, it says that the first line says white/blue. The second line says blue/white, all right? So that doesn't really make any sense. So what you're just going to do is you're going to cross out this white part there. And so this second line is just going to correspond to the pure blue wire, okay? So you would repeat the process I just showed you, but you would do it with the pure blue wire this time, okay? So the second line would be for the pure blue wire. The same thing goes for the other lines that end with /white. You just cross out that /white like I have here in the book, and you just use the pure color for those lines, okay? All right. So you go through this list and you put a check mark with all of the wires that are properly connected. If you find an open wire, you would just write open from one side to the other. And if you find any crossed wires or short wires, you would write those down in the bottom here, okay? Now I'm going to say that most of these cables have been modified so that there is at least one problem with them. So don't be surprised if you find an issue with your cable. And the cables are all different. So the issue you find on yours is probably not going to be the same as your neighbor's, okay? So that being said, a few of them don't have any problems. So if you go through the whole thing and there's no issues, that's okay too, all right? So, so that's the first part of the lab. So any questions about that? All right, and then the second part is about measuring resistance. So, so you're going to get 5 resistors from the back. I'll lay out a variety of different resistors for you. And then you're going to write down the color code value for each one and then the actual value. So the color code value is the value that is listed on the resistor. So like that red resistor I had, you would write down the color code value would be 2,200 ohms. And then the actual value would be the value that you measure with the meter. So in our case, it was 2,190 ohms, okay? Make sure you include your units here. Remember how important it is to put units. Remember the spaceship that crashed into Mars because they used the wrong units? Make sure you write down units here. If you just write down 2,200, I don't know if that's ohms or kilo ohms or mega ohms or what. So make sure you write down your units when you're writing your values here, okay? And then that's going to be the end of the lab. So any questions about that? All right, then let me take attendance and then I'll let you take a short break here.